Polynomials are wonderful objects. The curves are very smooth, pleasing, and they may be computed very easily. And they can adapt themselves to various different forms and shapes. As a result, there is little wonder that artists and engineers who work with digital medium, they like polynomials very much for the purpose of designing, computer-aided design and computer-aided manufacture. For example, whenever you see a nice curved object like this, you can rest assured that such a thing is created by using polynomials. All these curves are created using polynomials. Or if you see the body of a phone, all these little curves, etc., they are always created using polynomials. What we are going to learn today has to do with use of polynomials for artistic designs. When you make a picture, when you draw a picture, generally you start with a scribble, the rough idea, the artistic scribble, and then once you are sort of satisfied with the scribble, you want to smooth out the lines. Now traditionally the artist would himself do this smoothing out, or maybe delegate this job to some subordinate, some apprentice, but nowadays this job is generally done by a computer. So the artist first makes the scribble on a piece of paper, scans it, and then uses the computer to carefully pass a smooth line. Now if you want to just draw that smooth line using a stylus or a mouse, you will not get that smooth a line, your hands will shake a little. So what you do is you employ polynomials for that purpose, so that you are guaranteed to have very smooth curves. Okay, let's see one such example. Here I have one picture, a scribble. It shows a little ground, a slight undulation, and a little house. I want to capture this using a polynomial. So first I will start with this thing, this ground. I will click here, here. I get 1 point, and then I click here. Okay, so I get the basic idea of the ground. Pretty good. So nice flat terrain. Okay, now I want to capture that little mound. I will get back here, click. Oh no, that just completely ruined it. In order to capture the mound, it completely destroyed the horizontal terrain that I had created earlier. And that is a problem with polynomials. Polynomials are kind of global creatures. If you change a polynomial even slightly in one place, it has got repercussions everywhere else on the real line. Just think of this. The only bounded polynomials are the constant polynomials. You jitter a polynomial even slightly, take a constant and change 1 point even slightly, what happens? As a side effect, the polynomial will shoot up to infinity or minus infinity as x goes to infinity or minus infinity. So even a slight change in one place will ruin the behavior in some other place. And that is something an artist can never afford to allow, simply because the artist works on one particular detail first, and once he is satisfied with that, he will move to the next part, and when he fixes that part, he does not want his earlier work to get ruined. For example, in our case, we had this nice horizontal terrain, and when I wanted to accommodate this mound, that horizontal terrain just was ruined. Now one technique to get rid of this irritating behavior of polynomials is to use different polynomials for different parts. Let's try it out here. So I have two parts. One part is this overall horizontal shape, and then I have this little mound. So first let me capture the overall horizontal shape. Okay, This I had already done, pretty good. But now I am not going to change this polynomial in order to accommodate that mount. I will employ a different polynomial for the mount. Let's try. I will click here and here and here. That's better. So the blue parabola will now take care of the mount, and the red line will take care of the ground. So I am not going to use all the blue parabola. So I will take it only from this part to this part, that is the red ground. Then I will take this blue parabola only for this part, and then I will continue back with my red line. Not bad. But there is something that I do not like about it, and that is this point. You see this point? Here the red line and the blue line, they meet in a corner. But my original picture did not have that corner. I want the thing to be smooth. The same thing holds at this point also. It is this smoothness, this flowing nature, which adds to the beauty of any design. Having kinks and corners are not good. Polynomials are good because they did not have kinks and corners. They were differentiable. But once I take two polynomials, once I work with piecewise polynomials, then at the junctions, there might be kinks. So how do we get rid of that? What is the best way to match two polynomials end to end? Matching two polynomials nicely, that is the question that we have to address carefully. Now when you have two polynomials, one is starting where the other is ending, there may be different scenarios. For example, consider this. Here is the first polynomial ending, and now the next polynomial starts. You can easily see that in this case we have the worst possible scenario. It is not even a continuous function. The values of the two polynomials at that point do not even match. There is a break in it. A better situation is when the two polynomials at least have the same value at that junction point, like this and this. Better. Now at least it is continuous. But still we do not have the behavior that we are interested in, namely smoothness. We have a little kink there. We do not want the corner. The remedy for that is to put one more restriction on the two polynomials. They must not only have the same value, but also must have the same derivative at that point, same tangent, like this. Now it will come and it will go very smoothly out. Better. So when we say continuity, we basically say that the zeroth order derivative must match. The zeroth order derivative of a function means just the function itself. So the values of the functions of the two polynomials must match. That ensured continuity. Then I say that the derivatives must match. That ensures smoothness. Well, what about making it even smoother? For that, we might like to have the second derivative matching as well, like this, and then like this. So it is very smooth now. Of course, visually it may not really look that different, but it is slightly smoother. And you can go on like that. You can even say, I want the third derivative to match, like this. Now, if you consider the second derivative matching and third derivative matching, then visually there is not much difference. You can always put more and more restrictions, higher and higher order derivatives matching, but for the sake of art, where visual appeal is the ultimate thing, no one would really go above matching the second derivative. But in principle, whatever discussion we are going to do, you can do up to any desired order of derivatives. So what we finally want to do is to make a function by piecing together polynomials such that the derivatives will match up to a certain specified order. Well, that is the main idea behind splines. This is precisely what is called a spline. To be more precise, a spline of degree k means A piecewise polynomial where all the pieces are of degree less than or equal to k and the derivative is continuous up to order k minus 1. You understand that the derivative is already continuous for every polynomial. So when I say that the derivative is continuous for the entire function, we mean that whenever two polynomials meet at a point, their derivatives must be equal, derivatives up to order k minus 1. That is what is meant by a k degree spline. Graphically, we have a situation like this. I am given some x0, x1, x2, x3, x4. They are not necessarily uniformly spaced. And we are also given this card, that is our spline card. So this spline card is a piecewise polynomial over each interval xi to xi plus 1. It is a polynomial. Suppose I say of degree k, then it's a polynomial of degree less than or equal to k, another polynomial of degree less than or equal to k, like this. In my example, I have got 4 different pieces, and I want these polynomials to match perfectly at these junction points. They must have same first k minus or 1 order derivatives for this polynomial as well as this polynomial. So the tangents must match, the second derivatives must match, etc., etc. And of course the value must match. That is a spline of degree k. These points are called the knots. These are called the knots. And in many applications, they happen to be just equally spaced. In some cases, they are already dictated by some physical constraint. In many cases, the computer scientist would himself or herself choose these points to suit some special needs. Now, the most popular case of spline is when k equal to 3. These are called cubic splines. And these cubic splines are used everywhere in engineering and all sorts of artistic softwares. So here, each of these parts is a cubic polynomial or a polynomial of degree less than or equal to 3. So if I call this interval 1, interval 2, 3 and 4, so here the polynomial would be like a1 plus b1x plus c1x square plus d1x cube. Similarly here, it would be a2 plus b2x plus c2x square plus d2x cube. And we need various conditions on these AIs, BIs, CIs and DIs such that we have the same value here as well as all the other things. So if I put this condition that this and this must have the same value here to ensure continuity, you can see that the condition will be a1 plus b1x1 plus c1x1 square plus d1x1 cube must match a2 plus b2x1 plus c2x1 square plus d2x1 cube. Now remember that the xi's are already given to us. As a result, the relationship that we get is actually a linear relationship in terms of the coefficients to be determined. So we are given the xi's and we are trying to find the AI's, BI's, CI's and DI's. So the condition that I need continuity here will give me a linear equation, a homogeneous linear equation in terms of the AI's, BI's, CI's and DI's. Similarly, when I equate the derivative, first derivative here with the first derivative here, I will get another homogeneous linear equation in terms of all these AI's, BI's, etc. Now here I also have another thing that is given to me. I am also given the heights of these points. So someone tells me what are the values. So I have to also equate them with the values. So basically I will be doing like this: a1 plus b1 x0 plus c1 x0 square plus d1 x naught cube, that has to be y naught. Y naught is also given to me. So this also gives me a linear equation, but this one is non-homogeneous. There is a constant term involved. Remember, my unknowns are the ai's and bi's and ci's. So I will get how many conditions? 1, 2, 3, 4, 5 conditions, because I must match these values. And here I get one equation, here I get two equations, because this end must have height y naught, and this end also must have height y naught. So two equations here. So basically I get two conditions. Let me just write down. I get one condition here, I get two conditions based on only the continuity part, and then two conditions here, one condition here. Now I will look at the derivatives. I have only one restriction here, the two derivatives must match. The value of the derivative is not given to me. All that I care about is that the two derivatives here must match. So I have one additional constraint. Similarly, here also I'll have one additional constraint, no constraint on derivatives at endpoints. I also need k minus 1, that is the second order derivatives to match. So I have get one more constraint, plus 1, plus 1, plus 1. So how many constants do I have in all? 4 times 3, that is 12 constraints, plus 1, plus 1. So I have 14 constraints. And how many quantities do I have to find out? 1, 2, 3, 4. So I need to find 4 quantities for this polynomial, 4 for this, 4 for this, 4 for this. So I have to find 4 times 4, that is 16 quantities. And I have got 14 linear restrictions for that purpose. Clearly, this is going to be an underdetermined system. One can check quite easily that all these 14 conditions in general will be linearly independent. So no condition is appearing multiple times in disguise, but still they fall too short. And for that purpose, one will typically put 2 extra restrictions. There may be different types of restrictions. For example, you might require that the derivative at the 2 points should be 2 given values. You might require that the second derivatives must vanish at the 2 endpoints. If you put that extra restriction, that is called natural spline, where the second derivatives vanish at the 2 endpoints. Some people will require a condition like this value must match that value, typically when you are trying to model a periodic function, and the derivative here should also match the derivative there. So that will also give you 2 extra conditions. So somehow you have more freedom, you can still use 2 more extra conditions, and then you can solve for all the ai's, bi's and ci's, and you can get what is called an interpolating spline, because it interpolates using a piecewise polynomial all these points. That is basically the story of spline. However, certain computational neatness may be achieved if all those xi's are equispaced. In that case, you can rewrite the entire system not in terms of those a1, b1, c1, etc., but in terms of the derivatives. So the derivatives that match, if you call them d1, d2, etc., if you write them down in terms of the derivatives, just a reparametrization of the thing, then it turns out that if you are working with equispaced knot setup, then the linear system is pretty nice. It is a very sparse matrix. It's what is called a tridiagonal matrix, where all the diagonal entries are 4 and the superdiagonal and subdiagonal entries are 1. And if you are putting those extra conditions as the natural spline conditions, then the 2 ends of the diagonals will be actually 2. Now, how you get this particular form? It's just a matter of a little algebraic manipulation. Pretty simple. If you want the details, just look up the class web page. I have given the derivation there. Nothing very profound. And since you are anyway going to use a computer, you really do not care about this neatness. However, the final form happens to be diagonally dominant. So you might like to use a method like the Gauss-Seidel or Gauss-Jacobi method, But most often you do not have a huge system, so you do not care to use all those special techniques. There are, however, certain special linear system solvers which are designed to work for tridiagonal systems. Those methods are not part of our syllabus. If you want, you can do a little Google search on them. Just one final point. Since polynomials are functions, as a result, their graphs can never be a curve like this. A curve that doubles back on itself where the same vertical line intersects it at multiple points. Now, when you want to use polynomials for artistic purposes, for engineering design, you often have to work with such curves. Then what we use is that we use a parametric form like this. If I have to model this curve, for each point I will write it in the form xt, yt. And I will take xt and yt to be polynomials. So when an engineer or an artist will use spline curves, he or she will basically use this form where xt will be one spline curve and yt will be another spline curve. So basically this entire curve will be split up into certain parts. These will be the knots, and you now understand why they are called knots, because it is like a smooth piece of rope and these are like the knots tied on it. And then over each part, xt and yt will be indeed typically cubic polynomials. And then again, so if I call this thing x1 and y1, here the part will be x2t and y2t. And we will require that the values and the derivatives of x1 and x2 should match up to second order. Similarly for y. And again here. So we are using basically a two-dimensional version of spline. And it is possible to generalize this to three-dimensional version also. Those are called spline surfaces. And when you watch a movie like Shrek, etc., all their facial surfaces, they are basically modeled using splines.